We've now talked about significant figures and what they are, those digits that we've actually measured. We know it's a 4, we know it's a 7, we know it's a 3. Insignificant digits are ones we put in the number. They might be very important. Writing 0.05 is different than writing 5. Those zeros are important for telling us something about the number, but they're not significant. And that when we write 0.05, we're saying we know something about the 5, we know how small it is. That 0 tells us that it's small, but it's not necessarily a measured number. Now, your calculator doesn't care about significant figures. If you type in your calculator the number, let's see, 82 in your calculator, and you hit enter right there, it's going to tell you, okay, that's 82 right there, great. But, sorry, I'm trying to get the right light on my calculator. But if I type in 82.000000, our significant figure rules tell us that all those zeros are significant, that we actually measured them. But if I hit enter, my calculator says 82, because that's what it is to a calculator. It neither knows nor cares about significant figures. If I type 32.3822 plus 48 into my calculator, and I hit enter, I get 80.3822, and that's mathematically correct. It's great. But when I think about that from a scientific perspective, I look at these two numbers, 32.3822. Wow, I've got 6 significant figures. 48, what do I know? Well, I only know 4 and 8. What I don't know is it 48.0? Is it 48.1? Or maybe it was actually rounded and it was 47.6. I don't know anything else about that next digit when I put it into my calculator. So when my calculator returns 80.3822, do I really know anything about that 3? Because if it was 48.1 in actuality, right, because I didn't measure that last digit, I don't know what it is, I didn't report it, then it would 80.4822. If it was 47.6, I would have gotten 79.9822. And so I would have gotten different answers from my calculator depending on what this next digit was that I didn't report in my original number. Can I assume that 48 just means 48 exactly and it's 48.00000000? No. You can't assume that about most numbers, because just because someone reports 48 doesn't mean they measured all those other digits. It probably means they measured the 4 and they measured the 8 and they don't bother measuring the rest of the things, which is okay, but our math needs to take that into account. So it turns out we can't report 80.3822 because we don't even know if that 3 is a 3, much less the 8 or the 2 or the 2 way down there so far past all the numbers we've measured. And there we know nothing about those numbers. So what are we going to do? Well, like I said in the last video, there's an analogy of measuring things where if you take and you're baking something and you measure exactly 1 teaspoon of baking soda, you like level it off, you make sure there's no dust around the edges on it. But then you're supposed to put a 2nd teaspoon in and you dump a big pile of it, you just kind of does your perfect little measurement matter anymore? No, right? Because even though that one was so precise and you're really sure that you got that one right, the second one came in and ruined all your good measurements, and now you have no idea how much baking soda is in there. Okay? So measurements in lab, when we do math with them, when we do things with them, go the same way. If we have one measurement that's very precise and we know a lot of digits, and we do something and combine it with a measurement that's very inaccurate, that's very all over the place, we only know 1 or 2 digits, then we are limited. We are limited in what we can say about the answer. So we're going to have to round and fix numbers that come out of our calculator. And there's 2 sets of rules for that we're going to deal with for now. Our first set of rules is what we do when we are multiplying numbers and dividing numbers. And this is probably 80 to 90% of what we do in this class, multiplying numbers and dividing numbers. And so what is the math that we have to do? When we're doing multiplication and division, here's what you have to do. The answer has the same number of significant figures as the number with the least number of significant figures. It sounds a little bit weird when you read it. The answer has the same number of significant figures as the number with the least number of significant figures, but examples usually clear that up pretty well. So what we have here is we have a few calculations where we typed it into a calculator. The calculator gave us one answer, and what we're going to do is we're going to have to fix that answer to take into account that we don't know anything. When we look at this 87, right? It's only got two significant figures. We don't know if that next digit is a 4 or a 5 or a 7 or a 3. We don't know anything about it. And so when we report the answer to this one, what we're saying in these rules is that since we only know 87 to two significant figures, we're only going to know the answer to two significant figures. 45.3 has three significant figures, but we always choose the lesser. And so we're only allowed to have two significant figures in our answer. And so what we have to do is round 3,941.1 to two significant figures. And if you remember how we did that when we talked about rounding, is we drew a box around the ones we wanted to keep. We checked the next one, and we wrote 39? No, not 39, right? You want the number that you round to have approximately the same size as the number you started with. So if I started with 3,900, I want to end at something around 3,900, and I got to bring those zeros down. And 45.3 times 87, although mathematically it's 3,941.1, that's perfectly mathematically correct. Scientifically, we're saying since we only know 87 to two digits, we don't know whether that's a 4 or a 5 in the 3,941. And so we can only report this answer with two significant figures and say, the best we know about this is it's 3,900. It works when we do a bunch of numbers in a row, not just two numbers. We can do 3 numbers, 4 numbers, 5 numbers, 500 numbers. We don't round at each step. We don't multiply 25.5678 times 0.0939, then round, then multiply, then round. That will get you wrong answers. You do all your multiplication and division all to the end, and then you do your rounding. So we're going to count significant figures here. This guy's got 6. This guy only 3, because those leading zeros are not significant. This guy's got 7 significant figures. We did that one measurement really, really well, but we're limited by this one. So we can only have 3 significant figures in our answer. We're going to draw a box around that guy. We got to round that guy up, and so we get 3.04. And scientifically, that's the best we can do. That's the best we can tell someone about this answer. What about our next one? We're going to take 100.00. We did that one very precisely, and we're going to divide by 6. Now 6, I'm assuming I measured it somewhere. I took a stick and I measured 6 inches, or whatever it is. So that's a measured number. It only has one significant figure. This guy's got 5 significant figures, but we're limited by our worst one. And so we can only have one significant figure in our answer. We put a box around there. The next number is a 6, so we round up and we write 2. Well, my first number was 16. Shouldn't round down to 2. I should round to 20, right? Approximately the same size. Bring down those trailing zeros before a decimal to get our number. So 20. And what's interesting is scientifically, it's absolutely true that if you take 100.00 and divide by 6, you get 20. Now, most people will look at you and think you're crazy if you tell them that, because 100 divided by 6 is 16.667. And they're like, you can't be at 20. But what we're saying is scientifically, that's the best we can tell you. We can't tell you any more information than that because we know nothing about the next digits coming after that 6. However, if you've got more digits, here we've got 5 digits, here we've got 5 digits, which means our answer should have 5 digits. And occasionally, you'll have to correct the numbers the calculator gives you to have more digits. How do we get this to have more digits? We're going to add a decimal point. Right? Because decimal points make all of those trailing zeros significant. So if I write 20.000, I now have 5 significant figures because all those trailing zeros are significant. And that 0 before the decimal point, this one right here, is still considered a trailing 0. It's not trailing after the decimal. It's trailing after the last non-zero number, which is a 2. All right, 36 divided by 2 is 18. Again, assuming somebody went out and measured these numbers, 2 sig figs on 36, 1 sig fig on 2. We only get 1 in our answer. We're going to round up because we have an 8 there, and we get 20. So 36 divided by 2 scientifically is 20. Mathematically, it's 18. So go around, tell your family, hey, I just learned in chemistry class that 36 divided by 2 is 20. And they'll tell you that you should drop your chemistry class. But don't do that. We have to talk about sig figs. We have to take into account what we do and don't know about our numbers. So that is multiplication and division with significant figures. There's a separate set of rules. Sorry, I didn't make this stuff up. There's a separate set of rules that we use for addition and subtraction that's different than the rules we use for multiplication and division. So what we do for addition and subtraction is the answer has the same number of, and it's looking pretty similar to our last one. Here we next say significant figures, but here we do not say significant figures. We say digits after the decimal. And not significant figures after the decimal, but digits after the decimal. You're literally just counting numbers, zeros and all. Same number of digits after the decimal as the number with the least number of digits after the decimal. So, multiplication and division, we counted significant figures. Addition and subtraction, what we're going to be counting is not significant figures, but number of digits after the decimal, whether or not they're significant. Okay. So here are some examples. 147.38 minus 53.1, you put in your calculator, it says 94.28. But notice, right, we don't know anything about that next digit in the 53.1. We don't know if it's 53.17, we don't know if it's 53.11. So do we really know anything about that last digit there? And the answer is no. So here we have 2 digits after the decimal. Here we have 1 digit after the decimal. We're limited by our least, so we only get 1 digit after the decimal. That tells us we have to round up for the 8, and so we get 94.3. Here's another funny one. Assuming the 1 is a measured number, if we take this guy, he's got 4 digits after the decimal. Here, he's got no digits after the decimal. So what's my answer? My answer is only allowed to have 0 digits after the decimal. So we keep the numbers. We're going to round up because that 5 tells us to round up. And so we end up with 3. And you can tell your family also that you learned in chemistry class that 1.5 plus 1 is 3. But scientifically, that's the best I can tell you. Because if I try to tell you that 1.5 plus 1 is 1.5, what if my 1 was a 1.3? Then it would be 1.8, not 1.5. So 2.5 and 2.8. So the best I can tell you is it's pretty close to 3. Sorry, best I can give you. And that's true. Occasionally, we do have to add digits. Here we've got 1 digit after the decimal. Here we've got 2 digits after the decimal. And so, oops, sorry, that was my next problem. But here, right, we only get 1 digit after the decimal. So we're going to keep that. 31.9, if we round that up, we got round this guy to 0, right, to 10, but then we have to carry that over there and we get 32.0. Like I said, in the last problem incorrectly, sometimes we need to add digits. This guy's got 2, this guy's got 2, which means the answer should have 2 digits after the decimal. And we can do that just by adding a decimal and putting zeros as we need to. So we get 80.00. So those are our rules for addition and subtraction. Here's a chance for you to practice. What's the answer to 47.35 divided by 8.14? And a hint, there's only some difference between the possible answers, so you don't even need a calculator. Shh. Try it out. What did you come up with? Division means we're counting sig figs. 3 on this guy, 4 on this guy. We are limited to that, so we want an answer with 3 significant figures, 5.82. How about the next one? You try it out. What are we going to do here? We're counting digits after the decimal. This one always tricks up people. How many digits after the decimal are in 0.0300? A lot of people want to say 3, because like there's 3 significant figures. But there's 4 digits after the decimal. Even though that leading 0 is not significant, that's not what we're counting. We are counting digits after the decimal. And so this guy's got 4. This guy has 3. We're limited to 3 digits after the decimal. And we get 4.183. Even if we added those numbers and we got 14, and we seem to get this extra significant digit out of that, that's okay. So 14.183 or whatever, we still keep 3 digits after the decimal. It does happen sometimes that when we add numbers, we gain significant figures. Just like sometimes when we subtract numbers, we lose significant figures. Here's another one. We've got 8.933 times 10 to the minus third divided by 4.05 times 10 to the minus fourth. Good one to put in your calculator and try out using the built-in scientific notation of your calculator. Go for it. Okay. Hopefully when you did that, you got something, on the order of 22. If you got times 10 to the minus 7th, that means you were entering in the number wrong into your calculator, not using the built-in scientific notation correctly. So if we know it's there, we've got division. Our only thing is to count sig figs. 4 here, 3 here, 3 in our answer is 22.1. Here's some more practice for you. Take a few minutes, try these ones out, and then unpause the video and see how you did. 2 sig figs, 4 sig figs. Let me blow that up. So we only get 2 sig figs. We draw a box. 25. If you went from 2,500, is it okay to go to 25? No, you got to bring down those extra zeros and get 2,500. Here, subtraction, we're just looking at digits after the decimal, 3 and 2. So we're only allowed 2, and we get 2.45. Here, division, we're counting sig figs, 2 and 3. We're only allowed here 2, and we get 2.3. Here, 4.325 is 3. Here's 3, which means we get 3 here, and we get 2.400. Adding those zeros at the end in order to get enough digits after the decimal. All right, what's our next slide here? It won't advance. There we go. What's the answer to this one? We've got 8.35 plus 7.093 divided by 4.1159. And hopefully you look at that and you're like, I don't know. You didn't talk about that yet, because I haven't talked about it yet. I wanted to bring it up in a specific example so we could see it. What do we do in the case of having both addition and division in one problem? And the answer is we do order of operations. So we do our divisions, multiplications first when we can. In this case, we're going to do parentheses first because that's our highest precedent. So we're going to do our parentheses first, and then we're going to do our division. And anytime we switch rules, so when we switch from multiplication and division to addition and subtraction, or vice versa, we have to apply the rules for what we're working on, then move to the next. So because I have to do this one first, I'm going to do that addition, and then I'm switching to division after that. I have to apply the addition rules before I do my division. So what does that look like? If I get my calculator out, I put in my 8.35 and my 7.093. I put that in my calculator there. I'm going to get that answer, and that is 15.443. So it's going to be 15.443 divided by 4.1159. So I've got to get that intermediate number. But what's really important is I have to do that intermediate number and do its significant figures because I'm about to switch to division. So I've got to do my addition sig fig work before I do my division. I've got digits after the decimal since I'm doing addition. 2 digits after the decimal is what I get here. So this is actually going to become 15.44 divided by 4.1159. So I can't just leave it in my calculator there like that because it's actually not the right number. So what I have to do is put into my calculator a new number, which is the rounded number, 15.44. You have to be careful about this one. These ones are tricky. We don't run across these ones very often. I'm not going to lie to you. It's not the most common thing, but I'm going to put in the other parts there. I'm going to hit go, and it gives me my answer of 3.7513 with more digits afterwards. But what I have to figure out is what digits do I keep. Now I'm doing division, and so I do my division rules. And my division rules are counting sig figs. I've got 4 here and 5 here, so I get 4, 1, 2, 3, 4, and I get 3.751. Okay, not usually what people expect from this number. They usually expect to get A because they have 3 significant figures in the 8.35. But when we do addition and when we mix it with other things, we can get some slightly surprising examples in there. All right. We learned how to do math with significant figures, how to make sure that our calculator, when it gives us these numbers with 17 digits afterwards, after the decimal, that we know which ones to keep. And we do this through 2 sets of rules. One for multiplication and division, where we count sig figs and keep the least number, and the other for addition and subtraction, where we count digits after the decimal and keep the least number. And we saw one example of a mixed problem where we had both addition and division. And there we learned do our order of operations, and anytime we have to switch methods, we have to do our significant figure work. So we'll run across that once or twice, but mostly we're going to be doing straight multiplication division or straight addition and subtraction. All right, thanks so much. Bye.